Okay, in 7.2, we're going to construct confidence intervals for the population mean. The sample mean is the best point estimate for the population mean, and we can construct a confidence interval to estimate the population mean using a student t distribution or a t-distribution. This is similar to the normal distribution we used in 7.1, but it was developed because the standard deviation of the population is seldom ever known when trying to estimate a population mean. And so the t-distribution has the general bell shape of the normal distribution. It does have a mean of 0, but it has a standard deviation that varies according to the sample size. And the bigger sample you get, as you can see, the closer the t-distribution approaches the shape of the standard normal curve. There are two requirements to check before we use a t-distribution to estimate the population mean. We have to have a normally distributed population or a sample size of greater than 30. However, it doesn't have to be a completely normal distribution to use this. It is robust against departures from normality. So as long as the population is fairly normal with no outliers, the t-distribution will work to get the confidence interval for the population mean. Okay, so we're going to go through an example to estimate the population mean of body temperatures. Here there's a data set with 103 body temperatures of healthy adults having a mean of 98.1 degrees Fahrenheit and a standard deviation of 0.56 degrees. We're to construct a 99% confidence interval to estimate the mean body temperature of all healthy humans and see what that suggests about the fact that we all know that the average body temperature is 98.6. Is that going to support that generally held belief? Well, let's get our parts together. Our sample size here is 103. And the degrees of freedom is simply the sample size minus 1. So 102 is your degrees of freedom. And your sample mean is 98.1. So maybe lower than we would expect. Our standard deviation for our sample is 0.56. Okay, then we want a 99% confidence level. So our alpha is 1 minus 0.99 or 0.01. What we really want is just the area in one tail of the t-distribution. So we took our 0.01 and divided by 2 to get 0.005. So now we need to find our critical number, just like a z-score, but this is a t-score. In order to do this on Excel, we're going to use a t inverse to tail. So we're going to use the function t dot inverse dot to t for two tail. We just need the probability. So we're going to put in our alpha level and our degree of freedom, which is 102. And once we have that critical number, we can find our margin of error, which is going to help us build our confidence interval. So the margin of error for the t-distribution for the mean, we're going to take our critical number and multiply it by a fraction of the sample standard deviation divided by the square root of the sample size. And if we're going to multiply this, we need our little asterisk. And let's find out our margin of error. See if I got it. 0.144. And then in order to create our confidence interval, we're going to take our sample mean, just like we did before. We took a sample proportion. We're going to subtract off our margin of error. That's our lower bound, 97.96, and our upper bound will be our sample mean plus our margin of error, 98.2. So we have 97.96 and we have 98.24. And we can see that we are 99% confident that the actual mean of the population of healthy adult body temperatures is in the interval between 97.96 and 98.24. Now, what does that suggest about the suggested what does that suggest about the use of 98.6 as the mean human body temperature? Well, it seems that to suggest that the actual mean may be lower than 98.6 because even the upper bound is lower than 98.6.